Quantum computers are going through a phase transition from lab proof of concepts to fully integrated systems that need to function as a real product, a real computer that needs to deliver value to end users. This is a really, really fascinating time to be in quantum computing right now. You know, it's this moment that all of these pieces come together, all of the research insights and ideas and the breakthrough demonstrations and results of the last decades come together to form these integrated systems and to fulfill what once was only a distant dream. So it's really, really exciting to be in quantum computing right now. But we also need to realize that, there's this huge challenge. This is a huge challenge to bring all these pieces together, to integrate them, to push the performance of the full system, and to productize it. This is a huge challenge which is no smaller than all of the biggest challenges that we've faced so far in the field. So today I want to walk you through an end-to-end example that will demonstrate both just some of the challenges that lie in the road ahead of us, as well as hopefully will give us all also some good motivation, some great feeling and good motivation to continue to push forward to realize these computers, because I think that this end-to-end example really will demonstrate that we can really get there. And we at Quantum Machines are working on the classical side of the quantum computer. We're not working on the quantum processor, the quantum hardware. We're working on the classical side of the quantum computer. And so in my end-to-end example, I'm going to focus on this, on the classical side, on the challenges that are in the classical side of the quantum computer. And I hope to also show to you that we at Quantum Machines, with our technology and solutions, are already ready to meet those challenges that lie ahead. Okay, so we're going to take this example, end-to-end example, which is sort of the killer app of a quantum computer. That's the Shor's factorization algorithm. And we're going to ask the question, can we run Shor's factorization algorithm on a fault-tolerant quantum computer in the relatively near term? And I'm focusing on fault-tolerant here because we also want to run it in the relatively near term. So of course, we're going to take the sort of smallest example of the Shor's algorithm. We're going to factorize the relatively small number 21, but we want to do it in a way that already integrates all of the essential ingredients in order for these applications so that we can scale it up to eventually factorize real large numbers of interest. So, and one of the key ingredients is, of course, to scale it up is quantum error correction. And so specifically, we're also going to focus on how to do this on a superconducting qubit-based quantum computer that's running the surface code error correction type. And this is, you know, we can, of course, choose another qubit platform or a different quantum error correction code, but I think that this example will really demonstrate the gist of the matter. Okay, so to factorize the number 21 on a quantum computer, we are going to use this circuit that you see up here. This is a very simple circuit, only 5 logical qubits and very few single 2-qubit, 3-qubit gates. You can write it on a piece of paper in a few minutes. But in order to run this fault-tolerantly on a superconducting qubit computer running the surface code, you first need to translate this to what we call the surface level implementation of the code. This is what you see here. And this is much more involved. There's a list of different requirements. I won't go into all of them, but the important things here is that we need about 1,000 qubits, physical qubits, and we need 13 times during this circuit, we need to perform what we call decoding-based feed-forward operations. So these are real-time decisions that we need to make on what operations we apply or we don't apply to our qubits based on very heavy classical compute-based decoding, error decoding tasks. And finally, you see here at the bottom, perhaps the most important thing here, the requirement that to begin with, we need to start with physical error rates that are down to 0.1% error rates, okay, per gate. So you see, to run error correction efficiently, we first need to lower the physical error rates significantly. Okay, so these are the requirements, and from these numbers we can also derive the requirements for the classical system that needs to run these circuits on the quantum processor. And we can categorize these requirements according to 4 different categories. The first is merely the scale of the system. We need thousands of channels, control and readout channels, to perform this application. The second category is analog specifications. In order to lower the error rates, the physical error rates that we mentioned, go down to the 0.1% error rates that I mentioned, you need very state-of-the-art analog specifications. The third category is classical compute integration. As I mentioned, we need to do these heavy classical decoding tasks in real time and make real-time decisions based on them during the circuit. And finally, and very importantly, the user experience or the ease of use. That is very important. We need these full systems to be highly programmable by software so that we can iterate over development cycles very quickly. This is actually really essential at this stage of the game. Okay, don't worry, this was kind of the most technical part of the presentation. It's only going to get better from here. Okay, so we at Quantum Machines, as I mentioned, I'm not here just to tell you about Shor's algorithm and how to run it on a quantum computer, but also to tell you how we at Quantum Machines are ready for that. At Quantum Machines, as I mentioned, we're focused on the control electronics, the classical side of the quantum computer. We're making the modules both at room temperature and at cryogenic temperatures that allow our customers and partners to build their full stack quantum computers and to aim to such ambitious goals as we're looking at today. We're very proud to be working with some of the leading and biggest players in the field. Some of them we cannot mention for obvious reasons. And we're very proud to be working with over 300 customers around the world and what they're being able to achieve with our technology and solutions. And our flagship product, the OPX1000, is based on our unique pulse processing unit technology, which we believe is really the overall platform that can meet these challenges that we looked at in our factorization algorithm. So starting from scale, the OPX1000 has the highest channel density available today in the market, the highest control channel density available in the market. Cutting-edge analog performance, which were particularly optimized to meet some of the most sensitive quantum gate implementations, how sensitive they are to these analog specifications. Unparalleled classical compute integration. This is actually Quantum Machines' claim to fame. We were the first to integrate complete general classical compute engines into the heart of the quantum controller to achieve quantum classical latencies that are the lowest in the market today. And finally, our ease of use, the user experience and our flexible programming environment, which is based both on our programming interfaces, intuitive programming interface, open source libraries, and also on our amazing customer success team, which I think combined together is really allowing our customers to move faster than their peers or their competitors. Combine that with our very exciting upcoming product that we're developing with NVIDIA, DGX Quantum. This is a unique technology that for the first time really integrates the control system of the quantum computer with the NVIDIA Grace Hopper superchip, which is really to push quantum classical integration to new limits. And we believe that this combined platform is really the way that our full stack quantum computing customers can start realizing quantum error correction at scale. Okay, so we're going to walk through these requirements kind of one by one and see how we can meet those requirements. So starting from scale, we saw that to factorize 21 on a superconducting qubit-based quantum computer running the surface code, we need about 1,000 physical qubits. Depending on the QPU architecture, you would need about something between 1,000 and 4,000 channels, control and readout channels. These are many channels, but actually our technology can already meet these requirements. So as I mentioned, the OPX1000 has the highest channel density. We have almost 27 control channels in a single unit rack, which means we can squeeze about 1,000 channels in a single rack, electronics rack, as you see here. So we can use between 1 to 4 racks of electronics to factorize 21 here. This is really cool and very important, but it's not enough actually to just have the highest channel density and the channel counts. We also need all of these channels to be highly synchronized and work together as a single team. They also need to share data between them in real time. And for this, at Quantum Machines, we developed unique proprietary technology, actually highly patented technology to synchronize all of these modules and channels to very high precision, and also for them to share data. That's how we can partner with some of the biggest and most ambitious customers out there, like Alice and Bob, and in fact many others, Kilimanjaro, C12, Dirac, Pascal, IROQ, Colab, and many others. Again, not all of them we can mention. And our customers really can push scale to new limits, and also performance at scale, which is really the name of the game. There's some more nice pictures. Okay, so this was the scale of the system. The next important category is analog specification. This is a complicated subject, but I just want to give you one example to show you kind of the challenges that we have to deal with. So this is an example of phase coherency or phase alignment between control channels. You see, we have all of these control channels that need to control the qubits, and we need them to stay very, very aligned to each other, okay? This is what we call phase coherency or phase alignment. But due to noise in the system, those signals in different channels of the system, they drift from one another. And so noise and drifts in the system can eventually cause the system to go out of range because those quantum gates are sensitive to these drifts, and we can go out of the range that above the threshold of these physical error rates that we mentioned, these 0.1 physical error rates that we need to implement, Shor's factorization algorithm. Here we looked at a particular gate, which is a parametric ISWAP gate in superconducting qubits, and we see that in order to meet these requirements, we need really, really good phase stability in the system, less than 14 millirads. That's how we measure it. And again, fortunately and not surprisingly, OPX 1000 can meet these requirements. We can really bring the system down to very low phase noise and phase drifts in the system so that we can be on this green curve that you can see here on the top right, and be below the threshold that we need to implement our end-to-end application. This is, again, actually, this is thanks to this proprietary and patented technology of synchronizing all the channels in the system. And moreover, in this example, we can actually use these embedded classical compute engines. This is already bringing us to the next category of classical computing integration, in order to correct those phase drifts in real time in the system. So the phase drift in the system can actually be monitored and be corrected using these classical compute engines in the system, so that we sort of, every time we continuously correct those phase drifts. This capability, which was already demonstrated by many of our customers, here you see these are frequency corrections. So you can correct phase drifts, frequency drifts, amplitude drifts. Here you see beautiful pictures from the Schuster Lab and also Seoul National University, how you can really stabilize the system together with a system which is very stable to begin with, really gives our customers the ability to both optimize the fidelity as well as keep it high and stable for very long times, which is what you need in order to run applications. All right. So this was phase coherency, or analog specifications in general. The next category is, of course, classical compute integration. We saw that we need, in order to run quantum error correction, to run all of these decoding tasks in real time. Right, in fact, what we saw is that we have all of these different decoding tasks. Some of them could be run in parallel and could be parallelized. So we need this architecture, and to orchestrate workflows on this controller-decoder architecture. The controller is performing the quantum gates and measurement. The decoder is grinding all the mid-circuit measurements to infer the errors in the system and the interaction between them. There are very demanding requirements here. We need both very low latency between the controller and decoder, as well as very low latency between the controller and QPU. Okay, so without going into too much details, we need both like classical compute engines and control flow capabilities in both of these components, controller and decoder. And so looking at the QPU controller side, this is actually Quantum Machines' claim to fame. As I mentioned, we were the first to integrate these classical compute engines into the heart of the system. with our unique pulse processing unit technology, we actually put classical compute engines into the same chip that is generating the quantum operations. And this approach leads to many new kinds of opportunities. This is a magnificent example from Professor Andrew Zurak, who's leading Dirac Quantum, a new startup in spin qubits. So Dirac is able to create those hot spin qubits. So these are spin qubits that can operate in temperatures above 1 Kelvin, which is really cool because we don't need to cool them down to millikelvin temperature. It's a big breakthrough. But in order to initialize those qubits at these high temperatures, they need to actually leverage the OPX capabilities and to do what's called algorithmic initialization of these qubits, where they use these classical compute engines and the control flow capabilities, the abilities of the controller to make real-time decisions to really initialize efficiently their qubits. This is another example from Professor Oscar Painter's lab at Caltech, where they also use the OPX real-time capabilities to reset and initialize their multi-qubit devices. All right, but this was the controller QPU side. Now we also need the controller decoder side. For this, our partnership with NVIDIA really is all about bringing this vision into reality. So by creating the low latency link between the OPX 1000 and NVIDIA's Grace Hopper superchip system, and by providing the software interfaces and software tools that allow to program effectively and productively these hybrid workflows over this complicated hardware system, we really believe that this gives now the platform that allows full stack quantum computing players to start implementing quantum error correction at scale. This also brings us to the last category, which is critical, and this is the ease of use and the software programmability. I think that this diagram says it all. You know, there's a huge difference whether you choose the wrong or the right software interfaces and software environment and tools in your way towards your ambitious goals. It cannot be emphasized enough. If you need to spend months and months to just tweak and change your decoder for every iteration where you tweak and change your decoder versus weeks, this can really determine the entire velocity of your progress towards your goals. So at Quantum Machines, we put a lot of emphasis in building those software interfaces, and now with NVIDIA also the integration with CUDA, which allows to really program these complex hardware systems with the hardware performance, but program them with critical user interfaces and programmability that allows to move faster in the development cycle. This is a very cool example for it. It's not yet using DGX Quantum. It's because DGX Quantum is not out there yet. From Professor Ferdinand Kumeth in Niels Bohr Institute. But this example already shows that you can really program in software very complicated hybrid quantum classical workflows, in this case fully in Qua, to perform this real-time Bayesian estimation, which is almost as complicated as some of the decoding algorithms that we see. So with that, can we factorize 21 on a near-term fault-tolerant quantum computer? Well, at least from the classical control side, I think the answer is yes, we're ready for it. And we can even know the answer, 3 times 7. All right, so with that, let me thank you, and I'll be happy to take some questions.
Thank you, Yonatan. We have a few different questions. I'm not sure we'll be able to cover all of them in the time, but we have one question in Japanese, so I'll try to do my best to translate. But this person has heard that the controllers, quantum controller equipment uses a lot of power, uses a lot of energy. So in terms of power usage and the scalability of these controller equipment, can you talk about the relationship there?
Yes, this is an extremely important point. So I think there are kind of maybe 3 or 4 numbers that are incredibly important for scaling up control systems. One is the channel density. Second is the price per channel. We need to lower price per qubit control down if we want to go to the millions of qubits. And finally, the power consumption is incredibly critical. Today, we're still not limited by that. I would say that the main platforms, out there, like if you want to control 1,000 qubits, you could do that with a very reasonable size system. Not as nearly as power consumption as some of the high performance computers out there. But if you want to go to the millions of qubits, that is in fact power consumption starts to become the bottleneck. You can squeeze more channels into a single unit rack, but at some point the cooling power that you need to invest in order to cool down the system would actually dominate also the cost. So actually lowering power consumption is incredibly important. I think that eventually the answer, so most of these systems are based on FPGA systems and individual D2As and A to Ds converters. I think that eventually there will be no other way other than going to developing unique ASICs in order to solve these power and cost issues.
Thank you. You actually answered a couple of questions that came up along the way. Unfortunately, we don't have, that's it in terms of time, but I hope you can find Yonatan later and ask him the questions directly for those of you who weren't able to get the answers to your questions. But thank you, Yonatan, again.
All right, thank you. Arigatou gozaimasu.